All right, let's dive right into this explainer. Today, we are embarking on a really energetic exploration of the invisible architecture that literally surrounds us every single day. We're going to decode exactly how all of our data travels from point A to point B. I mean, think about it. In an era completely dominated by cloud computing, massive remote work setups, and interconnected smart cities, understanding this physical and logical map is absolutely crucial. Whether you're just sending a quick email, streaming a show, or securing highly sensitive corporate data, there is a distinct shape, a topology, dictating every single move that information makes. Here is our roadmap for today. First, we'll tackle decoding network topology. Then, we'll look at the linear bus, the common star, the closed-loop ring, and finally, we'll wrap up with a flexible hybrid. Okay, kicking things off with Section 1, Decoding Network Topology, the map of the network. So network topology isn't just one static, boring thing. Broadly speaking, it's the interconnected pattern of your network components. But here's the absolutely crucial distinction we need to establish right away: the difference between physical and logical topology. A topology can be physical, meaning it literally maps out the hardware, the cables you can physically touch, the actual router sitting on desks. Or it can be logical, which maps the invisible path the data actually takes to travel, completely regardless of how those cables are laid out. It's kind of like a city. The physical topology is the paved roads, but the logical topology is the actual traffic flow. Grasping both sides of this coin is essential for any modern network architect. Moving right along to Section 2, the linear bus. Simple and direct. The linear bus topology is all about striking simplicity. Picture a single cable segment acting as the main highway that connects all the nodes and devices. When this setup has exactly two endpoints, we specifically call it a linear bus. Now, the absolutely mandatory components here, and you can't skip this, are the terminators placed at the starting and ending points of that cable. Without these little caps, the network simply won't function. They exist to stop what's called signal bounce. Basically, if a signal hits the end of an unterminated cable, it bounces right back and scrambles all the new communication coming down the line. It's a real mess. You might be wondering, why would anyone choose a bus setup today? Well, it's highly cost-effective because you need way less cable compared to other layouts. It's incredibly simple to understand, fast to deploy, and expanding it is a breeze. You'll actually still see modern iterations of this in really small, low-budget networks, or, surprisingly often, in legacy manufacturing floors, where a single control line just runs straight down an assembly line. However, relying on one single main cable for the whole shebang comes with some pretty serious risks regarding fault tolerance. Which brings us to Section 3. The common star, representing centralized control. The star topology is without a doubt the most dominant structure in use today. In fact, you probably have a variation of this running in your own home right now. In a star setup, all nodes connect directly to a central device, usually a hub or a switch, through their own individual cables. That central switch is the boss. It acts as a repeater and a very smart traffic director for all the data flowing through. And it's incredibly adaptable. It plays nice with twisted pair wiring, optical fiber, or even older coaxial cables. Because everything is intelligently routed through that central hub, the star topology boasts seriously fast performance and naturally keeps unnecessary traffic to an absolute minimum. Plus, it is a dream for IT teams to troubleshoot. If a cable goes bad, they know exactly which specific wire to check without tearing down the entire system. But the real game changer here is isolation. The failure of one single node does not affect the rest of the network. In an enterprise environment, that is massive. One unplugged endpoint isn't going to take down the entire accounting department. Let's actually put these two head-to-head for a second to really cement this concept. With a bus topology, you've got a single point of failure for the entire backbone. If that main cable gets severed or a terminator fails, boom, the whole network drops instantly. But with the star topology, if one laptop completely crashes or a cable gets cut, everyone else just hums along perfectly fine because that central switch is still directing everyone else's traffic. It's a night and day upgrade in reliability for any business. All right, Section 4, the closed-loop ring. Sequential equality. Now for a totally different philosophy of data transfer. Instead of a straight line or central hub, computers here form a literal closed loop. Each machine connects directly to the next, with the final one linking right back to the first. In this ring topology, data is passed sequentially in one direction, kind of like a high-speed relay race, often using incredibly fast fiber optic cables. What's super unique here is the power dynamic. Every single computer in this loop shares equal responsibility for managing and passing along the data.
Thanks to that sequential equality, all these computers act as either a client or a server to push the info along. And this creates an absolute tank of a network under heavy strain. The transmitting network is virtually unaffected by huge traffic spikes or by slapping more nodes onto the loop. The data flow just stays totally predictable and stable. That's exactly why you'll frequently see ring topologies acting as the heavy-duty backbone for massive college campuses, where predictable speeds under crushing loads are a must. It's cheap to install, and if the loop gets too big, architects just drop in repeaters to keep the signal strong.
So this brings us to a really fascinating crossroads. We've seen the cheap simplicity of the bus, the reliable control of the star, and the heavy lifting power of the ring. But let's be real, modern organizations are incredibly complex. What if you literally want the best features of all these different designs at once? How do you overcome the glaring limitations of just using one single shape for a whole global enterprise? Enter Section 5, the flexible hybrid, the best of all worlds. A hybrid topology is the ultimate logistical problem solver. It seamlessly mashes up multiple architectures into one ecosystem. You are literally combining two or more topologies, like a star and a ring, so they can coexist. Imagine having a classic star setup running an individual department, giving the IT guys easy endpoint management, and then having that star connect via a central hub into a massive high-speed ring backbone that serves the entire campus. You're strategically pairing up their distinct strengths to completely cover each other's weaknesses. The perks of this approach are just staggering. A hybrid topology gives an organization the ultimate flexibility to add new devices and scale out over time. Think of a global banking network, right? It can't survive on just one shape. It needs the star topology so local branch tellers can plug in easily, but it relies on a massive ring topology to link up its global data centers without traffic jams. By cherry-picking the best features, the hybrid approach drastically slashes the chances of a complete network blackout while cranking up overall speed and efficiency.
So, what's the big takeaway from this explainer? It's simply this. There is no such thing as a universally perfect network shape. Whether you go with a linear bus, a star, a ring, or a massive hybrid, it all comes down to striking the perfect structural balance. Network architects have to meticulously juggle the budget, the scale they need to hit, the physical layout of the building, and exactly how desperate they are for fail-proof reliability. The digital architecture hiding in our walls and under our streets is constantly evolving to handle more smart devices and exponentially faster speeds. Knowing these foundational shapes gives you the master key to understanding how it all actually connects behind the scenes. So I'm going to leave you with this. As our collective hunger for data continues to explode, how is your own network going to shape up? Thanks for learning with us today.